Can you hear me? Okay, so looks like standard 10 students have some practice paper today, so not sure if you are joining, but in case you have to drop early, that is fine. Anyway, the lecture is available on YouTube after I upload it. Okay, so I think we're almost done with the problems that we were discussing last time. The last problem was remaining, but I think somebody posted a solution of that on WhatsApp, and that looked good to me. So maybe just I won't go over the full solution, but just to illustrate the main idea about how we're supposed to solve that problem. And there can be some alternate solution also. So let me know. There's some issue, but anyway. So while I'm trying to fix the problem, just to go over the last time solution. So I think one idea which was tried was we have to split the number x as the fractional part and the integer part. And basically, as I showed last time, that we can prove that x has to be a rational number. So I mean, there are two ways to approach it. One was the non-graphical solution which somebody gave, and the other is the graphical approach. So I mean, both of them can be completed. Basically, in the and we are doing the same thing in both solutions, which is that in a given range. So for now, I'm just sharing the solution which you had posted. So so basically, as we considered. Yeah. So we started by resolving the original given equation into. I mean, I think the calculations which are done here are can be simplified to some extent. But anyways, I mean, the final conclusion is right that in this line, 2 times fractional part of x into integer part of x has to be an integer. So which means that the fractional part can be written as some integer upon 2 times the integer part of it. So basically, that is what we have to check. I mean, only one thing which was missing in this solution was that, I mean, so we get the general form that the fractional part has to be, as I said, some k upon 2 times the integer part of x. And so the number of such possibilities, if we count, I mean, basically we can count for every range of, I mean, the integer part of x can go from 1, 2, 3 up to n. And so for each such value, how many such values of k are possible? So that is what we are counting here, and turns out to be just a simple arithmetic progression. So 1, 1, 3, 5, 7, etc. But I think there's one extra term which you have to add for the first or the last term. So that is how you get the n square minus n plus 1 solution. So if you try to do the same thing in the graphical approach which I was talking about, basically as it turns out that in every range like 1, 1, 2, 2 to 3, 3 to 4, etc. So in each such range, you will find that exactly n minus 1 intersections are there. So the answer turns out to be 1, 3, 5. I mean, exactly the same series which is shown here, that turns out over there. So that is how that was supposed to be solved. So I mean, we are now done with the questions, and I'm just waiting for my tablet to come online. But just to talk about what I would suggest you to do next. So unfortunately, because we have to also spend some time doing the theory, so we have to sort of split our time between theory and problems. But I expect you to do a lot more problem solving practice. And I mean, right now we are focused mostly on only number theory problems, but you can do the same thing for other topics also. So geometry, algebra, and I mean, more and more you realize that there is a lot of overlap between the topics, and I mean, what you need to know or what you need to solve. So I mean, you'll start to realize that more and more that you can apply the same problem solving techniques in more than one situation. So, for example, one important technique which I hope you are observing these number theory problems is estimation. So, I mean, typically the problem comes down to some kind of trial and error making. But before you do the trial and error, you have to try to reduce the number of cases as much as possible. So, come up with some sensible bounds before you actually start trial and error. So, that is something that that is applicable for not only number theory but also other topics. So okay, so what I've done now is I've actually connected from my tablet. Okay, so I hope you can see the tablet now. Okay.
Excuse me, sir.
Yes.
Sir, can I leave the meeting at 10 o'clock as we are having MPI
Yes.
physics practice test?
Yeah, I know. So yeah, you can leave whenever you want. You can watch the lecture online later on. That is fine.
Okay, sir. Thank you.
Okay. Okay, so I want to start with prime numbers today. I mean, as such, if you ask me, the theory part of prime numbers is not that much. Yeah, okay. So hopefully you can see this now. So I mean, just to complete what I was saying last time about the graphical approach. So the idea is that for every range of values, if you take the value k to k plus 1, okay, and this is a open like semi-closed interval. So it is open at k plus 1 and closed at k. And if in this range, if you plot the LHS and RHS of the expression, so I mean the two sides of our expression are x square minus greatest integer of x square, and the other side is x minus x the whole square. Right? So if you plot both of these graphs in this range k to k plus 1, you will notice how notice how the RHS and how LHS give. So RHS, if you observe, I mean, in this range, k to k plus 1, the greatest integer of x is always going to be k. So this is just a quadratic kind of behavior. This is I mean, this is nothing but fractional part of x square. So I mean, this RHS will have the same behavior in every interval. So it's going to look like the same graph like this, going from 0 to 1 in every range. And now if you look at LHS, x square minus greatest integer of x square. So see how many stops it has. So see, LHS is also fractional part of x square. LHS is nothing but fractional part of x square. So, but the number of cycles that this expression will have will be much larger. So, if I draw it with a different color, at k it starts with 0, but basically every time x square, x square as a real number, whenever it crosses an integer boundary, the fractional part will reset. So, the graph will look something like this. So, it will have as many lines from 0 to 1 as there are integers stopped from x square to the next one. So, basically from k square to k plus 1 square. Again, RHS is open and RHS is closed. So from this range to this range, as many integers are there, for every such integer, there will be one such crossing that you will get. So basically, it simply comes down to counting how many integers are there in this range, and that is simply 2k plus 1. So therefore, the answer turns out to be just a sum of 2k plus 1 as k goes from 1 to n or n minus 1. So I mean, this is how also you can look at the problem. Okay. So yeah, I mean, both graphical and non-graphical approaches are there. I would say, I mean, non-graphical approach is more rigorous in some sense. In the graphical approach, you have to explain a bit more that why does every such line cross the black line exactly once? So that maybe need to be explained properly, but in theory, it can be done. Okay. Yeah, so as I said, try practicing more problems, try to document what are the key ideas which you are getting. So, I mean, congruences, divisibility, these are of course important tools, but coming up with sensible bounds like bounding or estimation is also a very important tool. And today we are going to learn about one more powerful tool which has come into the forefront more recently. I would say, like last 5-6 years, periodic evaluation. Okay, so I don't know if some of you might have already heard of this term, but they were not done prime numbers yet, so I don't know. But periodic evaluation is also going to be a very important tool in number theory. Okay, as we'll see today. Okay, so but before that, we have to talk about what are prime numbers. So I mean, I think everybody knows from school what are prime numbers, but just to give a formal definition. And as it turns out, there are multiple definitions of a prime number. So there is not only one prime number definition. So if there is some integer greater than 1, then all the following 3 conditions are equivalent. So the first definition which you all know is that P has exactly 2 positive divisors, 1 and P. Okay. And in some context, these are often referred to as trivial divisors because they are the sort of obvious divisors. So another way of saying is that P does not have any non-trivial divisors. Okay. So this is the well-known condition, but because of Euclid's lemma, we have actually one more condition which can be also considered as a definition, which may come as a surprise. That you may consider this as a property that for all A and B, I think better take positive. If P divides AB, then P divides A or P divides B. So this is a property of a prime number, can also be the definition. So exercise for you is to try and show if you have a number which satisfies 2, then it satisfies 1 also. So 2 and 1 are equivalent, has to be shown. Okay. There is one more condition which I will explain more about that today. But ZP is okay. So this is something that you must have, and most of you may not have seen before. So I'll introduce this notation also. Okay. So, but all 3 of them are equivalent, like criteria to decide which is a prime number or not a prime number. Okay. So, I mean, as a first step, can you give you some time to think? Can you see why the first and second definition are equivalent? That I mean, probably the first part is more straightforward. That if so, 2 tasks, right? So prove that 1 implies 2. That if there is some number which has only 2 positive divisors, then why should it satisfy property 2? And then you also have to prove the reverse. That if some number is such that for all AB, P divides AB implies P divides A or P divides B, then that P has to be has to satisfy condition 1. Only then they will be completely equivalent. Okay, so maybe I'll give you a couple of minutes to think about this.
Sir, why do we require that greater than 0?
If one of them is 0, something go wrong.
Then still P divides that 0 number, right?
True, right? Okay, okay. I guess we don't need that. That is, yeah. By the way, I hope my voice is coming clearly. I mean, I don't know if the tablet is also picking up my voice and my laptop, so there is no echo.
No, sir, it's clear.
Yes, Abdul.
Sir, I did it for the first case where we have to show that 2 happens if 1 is satisfied.
Okay. Yeah. So how do we do that?
Sir, if P divides A, then the condition is satisfied. But if P does not divide A, then the GCD of P and A, it should be 1 because
Yes.
P has 2 trivial divisors, and then by Euclid's lemma P divides P.
Yes, correct. So does everybody follow that? That this is directly from Euclid's lemma. That so if 1 is given, which means that P has only 1 and P as divisors. Now, if for let some AB be integers such that P divides AB. Now, if P divides A, we are done. So let's assume P does not divide A. So then the because P has only 1 and P as divisor. So GCD of P and any other number can either be 1 or it can be P, right? So GCD of A and P can be, it has to be belong to the divisors of P, right? So it has to be either 1 or P. And if it is not P, the GCD is not equal to P, then therefore the GCD is 1. Okay, which means that A and P are co-prime. And as soon as A and P are co-prime, therefore by Euclid's lemma, P has to divide the other number, right? So that was 1 implies 2. What about the reverse? Why should 2 imply 1? Yes, Raghav.
Yes, sir. So we know that I have proof for this. Why 2 implies 1.
Yes, yes, tell me.
We know that P divides P. And so we can write P divides P1 times P2, where P1, P2 are factors of P.
Right. So I mean, we are going by proof by contradiction. If possible, let P be factored as just P1 times P2. Okay.
Yes. And we saw P divides P1, P2.
Yes, correct.
But by 2, we have P divides P1 or P divides P2.
Correct.
Now say P divides P1. Since P1 is smaller than P, and P1 can be either 0 or P.
Correct.
But it
So
can't be
basically-
0 since it's a factor of P.
Yeah.
So hence it has to be P. And P2 will be 1.
Yes, yes, correct. So I'm basically when we maybe better to state it here when we say let P equal to P1 into P2. So obviously 1 into P is a possible factorization, but we want to make sure we're not talking about that. So we can say where both P1 and P2 are less than 1, less than P. Where so you can say 1 is greater than P1, P2 greater than 1. So we can make this assumption upfront because we are going by contradiction. Okay. So then, therefore, as you said, if P divides P1, then we know that the modulus of P has to be less than or equal to modulus of P1, but which contradicts our assumption. Okay. So I think that's all. The proof is complete here. Okay. So therefore, 2 implies 1.
Sir,
Yes.
I have a doubt in the definition. Can you just scroll up once a bit? No, sir. Okay, sir. So if we have specified here that P belongs to natural numbers and P greater than 1, then
Yes.
below that, can you just scroll down where we So here, do we need to specify writing modulus of P is less than or equal to modulus of P1?
I mean, because we are going to make use of this given factor at P1, P2 less than P. I mean, important thing I want to use here is that P1 is less than P. And here we are saying mod P less than P1, which is not possible.
Okay, sir. Yes.
Yeah, I mean, I think you all famously know that 1 is neither prime nor composite, so we keep it out of it. Anushka, you were saying something?
Oh, yes, I didn't get the last part of this.
Okay. So if by the second property, we can say P divides either P1 or P2. So without loss of generality, let's say P divides P1.
Yeah.
So I mean, whenever one, and here P is non-zero, so when one number divides another number, the modular have to be like this. So first, the divisor always has a smaller modulus than the dividend or the RHS.
Yeah.
So and whereas we are assuming that P is factorized as P1, P2, where both P1, P2 are less than P. So this is a contradiction, right? Here we are saying P1 less than P, and here it is basically P less than or equal to P1. So both cannot be true at the same time.
Okay, sorry, got it.
Okay, so these were the first 2 definitions, but let me talk more about the third definition, like what is ZP and why does it matter? In some way, we already introduced the concept of this Z field when I was talking about congruous relations as equivalent classes. So if you remember, we had talked about when we defined congruences, we said that I mean, if let's not consider prime number, let me consider any natural number n. Okay? So then we can split the set of integers as a set of disjoint partitions, whereas if I call it set 1 union, set 2 union, set n, okay, where SI is the set of all numbers, all integers, such that X is common to I and all. Okay. So basically, if like to take a concrete example, if let's say n is equal to 5, then we said that Z can be split into the sets like 0, 5, 10, 1, 6, 11, and of course the negative numbers as well. So we could split the set of integers into these 5 sets. Basically, each set has all the numbers which are the same remainder modulo 5. Okay. As it turns out, we can do arithmetic on this also, as what we did with congruence relations, right? So if there is if a number x is over here and a number y is over here, I can do x plus y, right? But what I'm going to introduce is much more powerful idea. Why don't I consider this whole set as if it's an object? Okay. So if this whole set, I mean, this is a notational, you can say oversimplification, but we typically denote this by the first element. So 0 is the first element. So let me denote this whole set by the letter 0 or the number 0. Let me denote this whole set by the number 1, etc. Okay. So I have only these 5 objects, 0, 1, 2, 3, 4. And they may look like ordinary numbers, but actually each of them is a set. So 2, when I write 2, I'm actually talking about this entire set of numbers, which are remainder 2 modulo 5. Okay. And the interesting thing is I can do arithmetic on the set itself. So I can say set 2, like set 1 plus set 3 equal to set 4. So as it turns out, we don't know how to add sets. That does not make sense. But the way we can define addition is that I take any element like the definition of addition. Okay, definition of addition of these two sets. Okay, and let not write 0, 1, 2, 3, 4 just yet. Let me call them something S0, S1. Later on, we'll replace them with 0, 1, 2, 3, 4. But for now, SI and SJ. So, what do I define SI plus SJ as? So, this is the algorithm I use. Take any number from. So, take any element of the first set and any element of the second set. Okay, add them. So this x plus y will also belong to some unique k, right? So then we are defining SI plus SJ equal to SK. Okay, so I take any element of the first set, any element of the second set, and add them. And whatever set that addition belongs, that is my answer. So SI plus SJ equal to SK. Anushka, we have a question.
Yes, sir. K can be equal to I or J also, right?
Yeah, it can be equal to. So only thing is k, for example, here we're talking about concrete example of 5. So k has to be one of the numbers 0 to 4. But yeah, it can be equal to I.
Yes.
So do you see if this definition is okay, or there could be some problem with this definition? What could go wrong with a definition like this? See, the thing is, I am saying take any element x of the first and any element y of the second. So, could it happen that if I choose a different x and y, my answer will be different? So, if let's say one person decides to take a number x1 from the first set and y1 from the second set, x. Okay, and somebody else decides to take a completely different set x2 and y2. Okay, will they land up with the same answer or different answer? Because the sum x1 plus y1 and x2 plus y2 may not be identical. So what if it happens that the first sum belongs to some k1 and second set belongs to k2, where k1 and k2 are not equal? Can this happen? Yes, Raghav?
Sir, I don't think this will happen because we're talking about remainders, right? So it will be in the form.
So any element of SI will be like of some say A mod phi, and any element of SJ will be B mod phi. And when we add them, we'll get A plus B mod phi, which will always remain constant.
Yes, correct. Okay, does everybody follow that? And specifically here, if you see how I created a notation, SI is exactly the set of all numbers which have x such that x is congruent to I mod phi. Okay, so the subscript itself denotes what is the remainder. So if x1 belongs to SI, which means that x1 is congruent to I modulo 5. And by the way, I mean, there is nothing special about the number 5. You can do this with any number. And x1 is congruent to I, and y1 is congruent to j. So if I add them, x1 plus y1 is going to be congruent to I plus j. And same number x2 plus y2. So basically, x1 plus y1 will be congruent to x2 plus y2. So the definition, this is something that we have to cross check, that the definition I am coming up with does not depend on the choice of which x and which y I take. So this is why this definition works. Okay, and same with multiplication also. So I mean, the same process I can use. Take a number from the first set, take a number from the second set, and multiply them. And whichever set that belongs to, that is my multiplication. So I'm defining addition and multiplication of the sets. Okay, so we have defined addition and multiplication of the sets. Okay, and as I said that every time writing SI is inconvenient. So instead of SI, I can just write the letter I. I mean, notationally, I think it should not create any ambiguity. Okay, so therefore, I define the set Z phi as the set of all these phi. So in the case of, if I were to write it S1, S2, S3, S4, this will be the 4 elements. But instead of that, I mean, for convenience, I'll just write it as 0, 1, 2. Okay. So this is what I call the set Z subscript phi. Okay. So in the same way, you can see that for every integer n, so for any integer n, I can define Zn as the set 0, 1, 2, 3 up to n minus 1, where addition and multiplication are defined as I mentioned earlier, modulo n. Okay. So now the question is, does this set have some interesting properties which are related to things which we already know? So for example, I mean, these are standard things which we do in school, which are called like properties of commutativity, associativity, and things like that. So for example, I'll leave this for you to cross check that addition is associative, commutative. What does this mean? That A plus B plus C is equal to A plus B plus C. So when you are adding three numbers, doesn't matter in what order you add them. Commutative, when you have two numbers, you can flip their order and the answer will still be the same. Okay. Then there exists a additive identity. Okay. So there exists a number 0, right? 0 plus A is equal to A plus 0 is equal to A, right? And there exists a additive inverse. Okay. What is the inverse? So there exists a
Opposite of A.
So for all any A, there exists a set number like minus A, such that A plus minus A is equal to 0. Okay. So when all of these properties are satisfied by the set, there is a special name for any such set. It is called a commutative group under that operation. Okay. So the word commutative is applicable only if the second property is satisfied. There are sets in which the commutative is not there, in which case we'll only call it a group, but in this case it's a commutative group under addition. Okay. What about multiplication? So in the same way, can you check if multiplication is associative, commutative? Does there exist a multiplicative identity?
For A not equal to 0.
Yes, and multiplicative inverse. Okay. So can you check if all of these properties apply for the Zn as it is, or we have to make some modification? Okay. So if I
Last
consider
one, we will have to add A not equal to 0.
For identity, you're saying?
No, multiplicative inverse.
Inverse. Okay, A not equal to 0. So here you are saying that for all A not equal to 0, there exists a inverse such that A into A inverse equal to 1. That's what you are saying?
Yes, sir.
Okay. But so I have to take some time and check whether all of these are true for Zn. So Zn, as I said, was that the same set 0, 1, 2, 2 and minus. So out of this, I think associative is straightforward. So I don't think there is much to take that. I think everybody can agree that associative will happen. And the reason why it happens is finally the way we are computing the numbers. That when I multiply two sets, I take integers from those sets and multiply those integers. And because integer multiplication is associative, so naturally associative commutative is no problem. What about multiplicative identity? There exists a one such that for all integers, A into 1 equal to A. Is this true?
It will be true for prime numbers, because we have said the multiplicative inverse one. During converses, we studied that if the seed of A and N is 0, then A will have an inverse modulo N.
No, wait, but I mean, even before going there, is the statement, I mean, the prime number consideration will come for the inverse, but even for multiplicative identity, do you see this is not, I mean, is this true always?
Yes, sir.
Okay, it is true for Z ones. Okay, so yeah. So multiplicative identity is also true. Yeah, but for inverse, if you think about it, and I'll give everybody some time to think, that depends on what is the value of n. You know, if you consider a value of n which is prime or composite, the existence of multiplicative inverse may or may not be true. So you can take some examples, like take for example Z6. Okay? So Z6 is 0, 1, 2, 3, 4, 5. And check which of these numbers have a multiplicative inverse. Firstly, I mean, A not equal to 0 is important. So we never look at 0 as a candidate. But for the rest of the numbers, which of them have a multiplicative inverse and which don't have an inverse? So you see, 1 has an inverse because 1 into 1 is equal to 1. So 1 has an inverse. 5 has an inverse because 5 into 5 is, 25, which is 1, right? So 1 and 5 are their own inverses. But I think you can understand why 2, 3, 4 will not have an inverse. Because, I mean, basically 2k congruent to 1 modulo 6 does not have any solution. This is something which we have seen earlier also. So there cannot exist a number k such that multiplying 2 by k will give you 1 mod 6. Okay, so if n is composite, then it looks like it may not work. But do you see that if n is prime, then such an equation will always have a solution? then for all a not equal to 0, there exists a number a1, a inverse such that a into a inverse equal to 1. Okay.
So, for 2, 3, and 5, it should work with me.
2, 3, and
5.
no, see 2, 3, and 4 will not have inverses, right? 5 has an inverse. 5 into 5 is 1.
Yes, but
5
for
to 5 is
2, 3
20.
also it should work, right?
No, we are going modulo 6, right? So modulo 6 it will not work. See, which number multiplied by 2 will give you 1 modulo 6? That is not possible. No, 2, 3
no,
are 6.
1 modulo 6. Yeah, 1 modulo 6.
Yeah, 1 modulo 6, not
But
5.
not possible.
Okay. So I mean, I hope you can satisfy yourself that for any composite divisor, there will be some contradiction. But for a prime divisor, like if n is prime, then there will exist such an inverse. That's a into a inverse is equal to 1. Okay, and this comes down to simply the fact that ak congruent to 1 modulo p. This will have a solution because basically the GCD of a and p will divide 1. Okay. So the conclusion is that I mean addition works fine no matter whether your divisor is prime or composite, but multiplication you have to be more careful. The inverse only exists if p is prime, and that is what I mean by so if for any integer n, so for any integer n, Zn is a field if or rather this is a general definition that any object is a field if it is a commutative group under addition, okay, and the set except the 0 element. So you keep the 0 element outside, then it's a commutative group under multiplication. Dot or into, but it doesn't matter. Okay. So the entire set has to be a commutative group under addition, and the entire set minus the 0 element has to be a commutative group under multiplication. So if these two conditions are satisfied, then it can be called a field. And this is just a definition of a field. So there is nothing to be proven here. So now given all this background, do you see why the third condition was added there, that P is a prime number if and only ZP is a field. So ZP is a field only if P is a prime number. Otherwise, everything else works out fine, but multiplicative inverse cannot exist always. Okay. And actually, there are more definitions also of prime numbers which are a bit beyond the scope of what we do here. But I mean, actually, it's related more to sort of cyclotomic polynomials, and I guess if you are interested in all of that, you can read what is called algebraic number theory. So that is the topic which will give you more idea. But I mean, interestingly, that there are multiple starting points to assume what is a prime number, and each of them leads to the other two definitions. Okay? So there is no unique starting point. Okay? But I mean, for most typical treatments in textbooks, you'll always find that we start with the first definition, that P has exactly two positive divisors. Okay. So I mean, primitive is the most important property of prime numbers, which gets used all the time, is the property 2. Okay, so property 2 that so if P divides AB, then P divides A or P divides B. So this is probably one of the most important properties, and even from the problem solving perspective, this is the important property. The other important property is, of course, the fundamental theorem of arithmetic. Right? The fundamental theorem of arithmetic, which simply says that for all integers, positive integer greater than 1, there exists a unique representation of two rearrangements. So always when you say unique, you have to consider that rearrangement is a valid operation. Okay. So up to rearrangement, there exists unique representation of as a product of primes. Where PIs are prime. Okay. So as usual, I mean, this is like, if you remember what we did for division algorithm, there are two parts. That first you have to show that there exists a representation, and secondly that it has to be unique representation. Okay. So I think intuitively everybody knows this property, but just for the sake of completion, it would be good for you to try and see how to prove this formally. And as I said earlier, why is this important to prove this? Because there exist domains where this is not true. So this property is called a UFD. UFD, which stands for unique factorization domain. So if you go to a bit higher graduate level textbook, the same theorem can be written as simply saying that Z is a UFD, which means that the Z is a unique factorization domain. And there exist domains which does not have this property of unique factorization. Okay? So before we understand those examples, we have to understand why in integers this happens. Okay? So maybe I'll give you 5 minutes to think about this. How do you prove existence and uniqueness?
Sir, can you explain what unique representation up to rearrangement means?
See, if I have a number like 6, 6 can be written as 2 into 3 and 3 into 2. But do we consider these as different representations? We don't, because rearranging the terms does not count as a new representation. So whenever I say unique up to rearrangement, it means that 2 reorderings of the terms are considered identical. Okay. And you will see that, I mean, this is instead of writing that whole sentence that if there are 2 reorderings, they are considered identical, up to rearrangement is a very short way of writing them. And you'll see this more and more in combinatorics problems. So, I mean, there's a bit of a sidetrack here, but just to explain how this up to rearrangement definition works. So, these two, let's say you're coloring a 4x4 board or a 2x2 board. Okay? So, this is equivalent to this under rotation. So if I take the first board, you say I can rotate it by 90 degrees to get this board. So these are, I mean, if I can ask you the question, find the number of ways to color a 2x2 board, the black and white. So here I can say find the number of unique ways up to rotation. Okay, which means that when I say unique up to rotation, it means that 2 rotations, I mean, a rotation of the same board is considered a same identical. So you don't count these 2 as separate, you consider them as same. And you can think of cases where up to rotation, up to reflection, etc., etc. You can come up with number of such conditions under which 2 objects are considered identical or distinct. So that is the significance of this notation. Yes or no?
And I think I got the first part of the proof, existence one.
Okay. I'll just give a couple of ways for others to try also. Okay, so I mean, one way which I can think of approaching this problem is using some kind of induction. Is that what you have done or not? Or
Yes, sir, strong induction.
Induction, right? And I think strong induction will be useful here, because basically the idea is you keep on taking away factors of the number until what you're left with is a prime number. So,
Yes, sir.
right? So what we want to show is that, so we are given, let there be some integer that going on. So first, because you have to apply induction, so induction, applying induction on n. So what will be the base step? You can simply take any, okay? And n equal 2 is itself a prime number. So I mean, there is nothing to be done. It's a trivial case, right? So nothing more to be said there. And in the induction step, and I think important, we are going to apply strong induction. Okay? The strong induction means that, so for the n, let us say it is given that for the numbers 2, 3 up to n minus 1, all satisfy the condition. Okay? All have a representation. We are not talking about uniqueness yet, but simply have a prime representation as multiplication of primes for a prime product. Okay, So now we have to show that n is also having the same property. So what do we say now?
If n is a prime, then we are done. If n is not a prime, it will have two factors n1 and n2 such that one less than n1 and two less than n.
Yes, correct. Right. So if n is prime, then n is itself its own representation. So there is nothing to be done. But if n is composite, so n can be decomposed as some x into y, where both x and y are non-trivial factors. So that non-triviality has to be used here. So x and y are both between 1 and n. So therefore, we can apply induction hypothesis, which says that any number between 2 to n minus 1 can be written as a prime representation. So therefore, x can be written as maybe p1 into p2 into some pr, and y can be written as q1 into q2 into qs. So xy, so n which is x into y can be written as p1 into pr into q1 into qs. Okay? So which are all primes. So therefore, so the existence part is done. That for any number n by induction, we can say that it will have a prime factorization. What about uniqueness?
Sir, I have a proof for uniqueness.
Okay, tell me.
So we can say n can be written as p1, p2 all the way to pr,
Okay,
and also as q1, q2 all the way to qs.
okay. So if possible, let n be written as p1 into pr and q1 into qs. Where pi and qr are both prime numbers.
Yes. So now we know that p1 divides q1, q2 all the way to qs.
Yes.
So by Euclid's lemma, p1 divides one of q1, one of q1, q2 all the way to qs.
Yes. So I
See,
mean, just to indicate one point here, we are actually using a generalization of Euclid's lemma, because Euclid's lemma is only for two terms, but I think everybody can see that if some p divides number of terms, p divides some a1, a2, ak, then it implies p has to divide one of them. So that's a simple extension of Euclid's lemma. Okay, so continue.
So say p1 divides q1.
Okay, so without loss of generality, let's say p divides q1. Okay.
So since p1 and q1 are both primes, p1
Yes.
has to be equal to q1.
Yes, so q1 has to be equal to p1. Right.
And similarly, you can conclude that all primes will be equal to sum of the other prime, one of the other primes.
Yes.
And thus
Right.
both the factorizations will be equal. Same.
Yeah, sure. So I mean, we can also put this in again in terms of strong induction, right? So again, if I mean, just to writing that continuing this way, we can simply say that now that we obtain q1 and p1 are common, I can just cancel both from both sides. So I'll be left with, so I can consider the number n upon p1 or n upon q1, which can be now written as p2 times pr or q2 times qs. Okay, and by strong induction, I can claim that this number, which is clearly smaller than n, must have a unique representation. Therefore, I mean, these P2, PR, and Q2, QS are identical. Okay? So I can finish the problem there itself instead of saying that continuing in this way, we keep on showing P2 equal to Q2, etc. So you can finish the problem this way also. Okay, so and I hope you see how induction can be used to shorten the chain of reasoning. That try to avoid saying that continuing like this, we get something. We can use induction to directly come to the n minus 1 step.
Sir,
Yes.
if we proceed by Raghav's solution, like non-induction one, at the end we will also have to like add like what we did showed that that p1 to pr is a subset of that q1 to q.
Yes.
So you will also do the reverse way, right? Like
Yeah, I mean, you might be left with a situation where the PIs are over and still you have some leftover QI. So, I mean, we are not talking about R and S comparison, rather, right? So, if R is less than S, then you might land in the situation where the PIs are over and still the remaining S minus S terms of or S minus R terms of QI are left. So, we may have to handle that final corner case also, right? I mean, that will be trivial because what will be left is equal to 1 is equal to a product of some prime numbers, R plus 1, R plus 2. So that will obviously be a contradiction, but that final statement has to be made if R is less than S and similarly if R is greater than S. So we have to take care of that final case. Okay, but I think we avoid all of these problems if we use strong induction. Is that correct? Okay. And so, I mean, typically we don't write the factorization as P1, P2, PR, etc. We write what is called a canonical representation, where we combine all the exponents together. Okay, so more typically, it's the way we write is n is equal to P1 raised to K1, P2 raised to K2, PR raised to KR, where now the PR are distinct primes. Okay. So this is what is called a canonical factorization of. Okay, so I think we all know this. So at this point, I think also allows us to come with an alternate definition of GCD also. So if you have two numbers, if let's say you have number m, which is P1 raised to K1, P2 raised to K2, PR raised to PR, where Ki greater than or equal to 0. So importantly, I allow the Ki to be 0 also. In the canonical factorization, we actually say Ki has to be positive. Okay, because we don't want, I mean, we can always multiply a number with something raised to 0 without changing the value. But here specifically, I am allowing extra Ki greater than or equal to 0 to be there. Because it could be that the two numbers don't have the same set of prime divisors, right? So P1 raised to L1, PR raised to LR. Okay, so in case there is some prime number which is missing from the other term, we can equate that by just adding the PR raised to 0 kind of term. Okay, so if we have two numbers like this, then do you see what we can define the GCD here? Or rather, we can say that GCD of m and n will be equal to which number?
Can I tell?
Yes.
P1 raised to minimum of L, that is lambda or L.
L1, L1, and
L1 and K1 and
yes.
P2 raised to.
Correct. So the GCD will take the minimum of the two exponents. And I think this is something again which you study in school, so it should not be a surprise. Again, I will not spend time trying to prove this. I think you can try to do this as an exercise. That this is the GCD and same for LCM. LCM is the thing but the max. So you take the max of all the exponents, and that will give the LCM of the two numbers. Okay. And so do you see that this gives you one more proof of the fact that m into n is equal to GCD into LCM? Because if you look at it term by term, like check what is the exponent of P1 on LHS and P1 on RHS. Okay. So for any prime P1, in fact, we have to do this for any prime P, right? So this is where we are going to head into a territory called periodic evaluation. Okay? So we are going to sort of transition into that. But just as a small example of this, what we can do here is show that m into n equal to GC into LCM, because for any prime P, what is the exponent of LHS? So exponent of LHS, or rather I should say exponent of P in the factorization of LHS. So it's a very big term, exponent of P in the prime factorization of LHS is equal to the exponent of P in the prime factorization of RHS. Okay. So you can see that, right? Because if there are two possible cases. If the prime P is in the list of P1, P2, PR versus it is not in the list. So if P is not in the list of P1, P2, PR, then it does not occur on either of the two sides. So the exponent is 0 in both cases. But if P is one of the prime numbers, let's say we are talking about the first prime P1. So what is the exponent of P1 on the LHS? Because m into n, which means that the exponent of the LHS will be simply K1 plus L1. And on the RHS, it will be the min of K1 plus L1, K1 comma L1 plus max of K1 comma L1. And you can check that for any two numbers, their sum will be equal to the min plus max, because I have two cases, right? Either one of them is smaller than the other one, or they are both equal. But in both cases, this is going to be equal. So for every prime number, if the exponent of LHS and exponent of RHS is the same, then the numbers themselves will be equal. And this is because of the uniqueness of prime factorization. Arnav, you want to add anything?
Oh, no, sir. No, sir.
Okay. Okay, so do you see how we can use the exponent, comparing the exponents of a prime number as a tool to solve some kind of problem? And this is what we call the periodic evaluation, because we're writing this whole expression, exponent of p in the prime factorization of LHS. This is too big to write every time, so there is a notation for that, and that is called VP. Okay, so VP is a new function which I'm introducing. So for any prime p, we define VP as a function from Z to, I think we have to exclude 0. So you cannot have 0 in the set. But all the non-zero numbers, you can have a mapping from Z to Z, where we define a VP of any number is this whole expression, the exponent of P in the prime factorization of, I take modulo n, because for negative numbers, it may better to write as a modulo. Okay. So the exponent, the largest power of P which occurs in the prime factorization of a number is what we define as VP. And this kind of evaluation is called p-adic evaluation. So in other words, the p-adic valuation of the number n is that largest exponent. So I mean, just to give you some examples, I mean, what is V3 of 18 is 2, because 3 square 9 is the largest power of 3 which occurs in the factorization of 18. Okay. So this periodic valuation has some very useful properties which we can study at some point. In fact, I'll need some time to prepare for this, because even I'm new to this, so I'll talk more about periodic valuation in the next lecture, okay? Because I'll have to do some research. But in your own, you can also try to Google this periodic valuation, and you'll come with all sorts of interesting properties about this periodic valuation. And more recently in Olympiad problems, this is more and more frequently seen that this can be used to solve a lot of problems, especially at the higher level, like INMO and IMO onwards, but very good tool to know. And as it turns out, I mean, here I defined periodic valuation for integers, but you can do that for rational numbers also. So that is like a much more complex topic. So we will not go there, but it is possible to define periodic valuation for rational numbers also. Okay. But I mean, leaving that aside, if you remember, I had given you one exercise a long time ago when we did GCD and LCM. So when we said that m into n equal to GCD into LCM, I asked what is the generalization for 3 numbers, if you remember. So if I have some 3 numbers A, B, and C, then what about, is it true that the GCD of ABC into the LCM of ABC, and here I'm using the square bracket notation for LCM, is equal to ABC?
No, sir, because
I think we had found back then that this is not true.
yes,
And
yes.
the exercise I had given you was, can you modify this property in some way to make it true? So does anybody have any idea what can be a slightly different statement which will be true? Yes, Anushka.
Yes, so we've seen that GCD of A comma B comma C will have the exponent. So let A, we'll define A, B, and C as say P1 to the power alpha 1 into
Yes.
P2 to the power alpha 2.
Yes.
So on up till Pk to the power alpha k, and then B as P1 to the power beta 1, and then and so on, and then C as P1 to the power say gamma 1.
Okay.
So we have the GCD of ABC will have like the exponents of P1 will be the minimum of alpha 1, beta 1, gamma 1.
Correct.
And the LCM will have the maximum of alpha 1, beta 1, gamma 1.
Correct.
Now, so like we have only 2 numbers. So let like without loss of generality, we can say let the minimum be alpha 1 and the maximum be gamma 1. So when we multiply 2 numbers, it should be like such that the power is the minimum and the maximum. So over here we won't be able to multiply B. We can just multiply A and C. So for that we'll have to see the power, the exponents of A, B, and C of like the prime numbers, and then we'll have to check which is the minimum and which is the maximum.
Okay, but so the problem is for first prime number P1, it could be that alpha 1 is smaller than gamma 1. But for P2, the reverse could happen, right? So if you just multiply A and C directly, it will not match up for all the prime numbers.
Right.
You see the problem? I mean, for every P1, alpha 1, beta 1, gamma 1 order can be different. So which is the minimum, which is the maximum can keep changing.
They're like we have functions for maximum and minimum if we could have some function for the middle ones also, then we could do
So
some.
then you can say ABC, GCD of ABC into LCM of ABC into that third quantity. The whole product is equal to ABC. Something like that.
Yes, sir. Yes, sir.
That is true.
Into the median of ABC, like the middle value.
Okay. Why don't you try a few experiments? I want you to observe. So for all, I want you to observe. Take a few examples and try to observe for all A, B, and C. Observe the value of, and I mean, it is up to you to take creatively good values which will give you useful data. ABC upon the GCD of ABC. So can you see some pattern in these numbers? Okay, do a few experiments and try to come with a conjecture. So, for example, one useful experiment, I mean, it's all up to how you choose ABC cleverly to get useful information. But one choice could be you want to consider a case where there is something common in every pair of the numbers. So, A can be 2 into 3, B can be 3 into 5, C can be 5 into 2. So, pairwise, there is something in common. So, it's 6, 15, and 10. Okay, so, ABC upon GCD of ABC. So the GCD is 1 actually, so that one will go away. So this is simply the product of ABC. What if ABC were composed of 3 different primes altogether? Then what happens? Let's say A is 2, B is 3, and C is 5. Then also
Yes, so that is again 30 by 1.
Yeah, I'm trying not to reveal the answer. What hint can I give? Okay, the hint is you have to change this term somehow. Okay, so this you have to find the LCM of 3 numbers, but not ABC. You have to choose some 3 different set of numbers such that the product will turn out to be equal. So what should this term be? That is the question. Okay, and let's do everything periodically. Okay, that's a new phrase that we start to use. Let's do periodic evaluation. So let's consider some.
Sir, can you give 2 minutes? I think I'm getting something.
Okay, sure.
No, sir, I did not get.
Okay. So I mean the hint I'm giving is look at it periodically. So let's say pick some prime number p. Okay. So I already told you that find that missing term. So find that missing term x such that the GCD of ABC into that x will turn out to be the product ABC. So now let's pick some number p which is a prime. Okay. And instead of now the advantage of periodic notation is that I can ignore all the other prime factors and just look at it from the lens of what is the exponent of p. So as Anushka said earlier, let's say A has the exponent p raised to alpha and everything else we can ignore. Okay, so similarly beta and gamma. Okay, so B has some beta and C has some gamma. So then in this case, periodically RHS is nothing but the if I just look at the exponent, so VP of ABC, the exponent is simply alpha plus beta plus gamma. Okay. On the LHS, the exponent of this, the VP of this term will be simply the minimum of all the things. So minimum of alpha, beta, gamma. So whatever this x is, it has to have the what should come as the exponent of that. So it should be raised to alpha plus beta plus gamma minus the minimum of alpha 1, alpha beta gamma. Okay, that is what this x should have. See, why did the property work for two numbers? If you carefully observe this periodic notation, when we compare the exponent of the LHS and RHS, see LHS periodic relation we know it is K1 plus L1, but RHS was minimum of K1 L1 plus maximum of K1 plus L1. The important thing is that if K1 is the minimum, then L1 is automatically the maximum. So this inverse relation that whichever is the smaller one, it forces the other one to be the greatest one. Yes, Raghav.
Yes, I think I got what would be in the bracket ABC instead of ABC.
Okay, tell me.
It should be AB, BC, and CA.
Yes, correct. So this is the property. The GCD of ABC into the LCM of BC, CA, AB. So taken two at a time. Okay. So now can you think about why this works? Why is this true? Again, if you look at it from the periodic notation, it will make sense very quickly. Yes, Raghav.
Yes, so like if you're taking the LCM, it would be from the periodic notation for any P, it would for some P, it would be the maximum of alpha plus beta, beta plus gamma, or gamma plus alpha.
Yes. And the important thing is that if alpha is the smallest out of the alpha beta gamma pair, then beta plus gamma will be the largest out of that triple, correct? So if let's say if A is P raised to alpha times something, so I don't write the whole thing every time. So actually that is where we develop the periodic notation. Let me use that. So if the VP of A is alpha and similarly beta and gamma, okay, then for the first bracket, the VP of this product, the GCD, will be the minimum of alpha, beta, gamma. And the VP of the LCM, the second bracket, this one, will be maximum of alpha plus beta, beta plus gamma, and gamma plus alpha. And now do you see how the same thing which we use for two numbers is applicable here? Whichever of this is the smallest one. So if alpha is the smaller one than other two, then automatically the complement of alpha, which is beta plus gamma, will be greater than the other two summations. Okay. So for every prime, what will happen is the first will give you one term, let's say alpha. The GCD will give you alpha, then the LCM will give you beta plus gamma, and together the exponent of the LHS will become alpha plus beta plus gamma. So no matter which, in some for other prime, beta could be the smallest, doesn't matter. If beta is the smallest for that prime, then alpha plus gamma will be the greatest. So this kind of complementation is happening. That is why this turns out to be true. Okay, does everybody follow this logic?
Yes, but I had a comment on this. Yes, sir. So it can also be like LCM of A comma B comma C multiplied by the GCD of BC, CA, AB, right?
Exactly. Yes, correct. So in fact, you can do the reverse also. So you can take LCM of ABC and GCD of ABBCs. This will also be. This. Okay. And once you understand this pattern, you can generalize this to a really big notation. So you can do this for A1, A2, AN also. So I think if you have A1, A2, AN, you see that the GCD of this into the LCM of everything but one. So let me, for convenience, let me denote, let the product of AI be denoted as capital A. So then capital A upon A1, capital A upon A2, capital A upon AN, this product will be equal to A. Okay, so very similar logic can be used to prove this also, and so many things actually. Okay. So, but anyway, I mean, this was like a quick demonstration of how periodic evaluation can be useful in some cases. As I said, let me think more about how I want to teach periodic evaluation next time, because I would like to come back with some problems also from RMO, IMO, where you can apply the periodic evaluation. But returning to the theory of prime numbers again, so pretty much the only thing left to be shown is what we call infinitude of prime. So the fact that there are existing infinitely many primes. Again, a very famous classic proof by Euclid, which is like one of the most legendary proofs because it is very simple. Okay, so there exists infinitely many primes. I think this is a proof which others might also have seen somewhere. It's not that new. It goes by contradiction, right? So if possible, let there be finitely many primes. So let P1, P2 up to Pk be all the primes. Okay. So if there is only a finite list of primes, we have to come up with a contradiction. So we just have to construct one more number. We construct that new number as the product of all the primes, which we know so far, plus 1. Okay. And this itself is sufficient to prove that basically what will happen, either n is itself a prime. So it will be a new prime which is not in the list because n is definitely greater than all the pi, right? So if n is a prime number, it's a new prime number. So we have extended our list by 1, which is a contradiction to the finite evolution. Or if n is composite, then also you see a problem, right? If n is composite, which means that there exists some prime which divides n. And that number is already in this list. So you can see that this will imply that p divides 1, and which is a contradiction. So either way, we come with the contradiction that there cannot be finitely many primes. Okay. So this is one of the classic proofs by Euclid to show infinitely many primes. But over time, so this was just about existence of primes in general. There has been a lot of work done in terms of multiple directions of approach. Firstly, that here you are taking all natural numbers, but what if I took a subset? Like here can be one more question that prove that there exists infinitely many primes of the form 4k plus 3. Okay. So this is like a slightly modified exercise that not only are there infinitely many primes, but this 4k plus 3, which is an arithmetic progression, also has infinitely many primes. And this, I think we know enough theory to do this problem. And similarly, a few other problems, like for example, 6k plus 5 also is infinitely many primes. The most general statement of this type is that if there are two positive or rather co-prime numbers, if there are some co-prime numbers A and B, then the AP AK plus B for k integers. Okay, so this is an arithmetic progression AK plus B also has infinitely many primes. Okay, and this is it looks like a problem of the same family, but it is much harder. Okay, so this is actually
We'll have to first show the existence of one of the primes first.
Which one are you saying?
In the AK plus B1, we will have to first show that one of such primes exists.
Yeah, we have to. Is that doable? I've never tried it.
But I'm not sure. Like if we can show that one of such prime exists, then it's, I think.
No, but even if one prime exists, what is the guarantee that there are infinitely many primes in that case?
Yes, sir.
And I don't know if that showing out one prime exists is also that simple or not. I've never tried it. Okay, but this is called Dirichlet theorem and requires a lot more advanced number theory and even calculus, and so that is where the algebra and number theory start to blend into each other. So we are definitely not equipped to do anything like that, but we can try these problems. So 4k plus 3 type numbers and 6k plus 5. Maybe I'll give you a couple of minutes to think about both of these. That why will these two APs have infinitely many primes? Somebody was saying something. I don't know. Okay. So 4k plus 3 already know examples like 3, 7, 11, 19, etc. So these are all 4k plus 3 type times. But can it be that after a point you still have prime numbers, but they are no longer of the form 4k plus 3? Because I mean, it has to be an odd number, that is fine. So it can be 4k plus 3 or 4k plus 1. So why not after a point all the prime numbers are of the type 4k plus 1 only? You don't have any primes of the type 4k plus 3. Is that possible? So if you observe how we did Euclid's proof, that if assumed if possible let there be finitely many primes p1, p2, pk, and from that we constructed a new number n. We are free to choose this number n anyhow we want, but it has to help us prove that the number of primes are not finite. There is one more term which is not included in the list. In the same way, let's say take 4k plus 3. So if possible, let there be a finite list of primes. So let p1, p2, pk be all the primes of the type 4k plus 3. Kk is the pt. Okay, so these are all the primes of the type 4k plus 3 form. So can you think of how to construct a new number which will be forced to have one more prime of the type 4k plus 3? Yes, Raghav.
Yes, so we'll just take the 4 times the product of all primes plus 3.
Okay. So what
And
can you say
then-
about this number?
So we know that none of the, we know that 3 won't divide this number.
No,
Because-
actually 3 is there here, right? 3 is also one of these numbers.
So then if we can exclude 3.
Okay, so we'll start the number list from written. So the first number is greater than 3. So 3 we consider as a trivial divisor. So 3 is not here.
Then
Okay.
no, yeah, then 3 won't divide this number.
Yes.
And no other prime can also divide this number because it's not a factor of 3.
No, but this list only has primes of the type 4k plus 3. So there could be some factor of the type 4k plus 1.
So I don't understand.
No, what is your claim that no prime divides n?
No prime pk would divide this number.
That is true. Okay, so no prime, no pi divides n. Okay. Then
So
what?
no, so this number would be prime, right?
No, it can be composite. I mean, you can multiply. I mean, your argument I don't think is complete there. Why is this number prime? It could have factors of a type 4k plus 1. Yes or no?
Sir, let's assume there are finitely many primes of the form that 4k plus 3.
Okay.
Then we multiply all of those and add 3.
Hmm.
So multiply all of them by 4, all of them and multiply by 4 and add 3. So
Yes.
we get
So
that
I think up to this step you have done the same thing which Raghav is doing, right? So you constructed
Yes,
this
sir.
number n. After that, what will you do?
So now this is an odd number, so it will have only odd factors.
Yes.
So if it has only odd factors, then one of the factors must be of the form 4k plus 3.
So that is an important thing which you have to show as a lemma first. Why should it have
Because
a
if all are of the form 4k plus 1, then
yes,
by multiplying by modulus multiplication, we get that all of them are just, it is final answer is just 1.
yes, correct. That was the important step. So if let's say let the prime factorization of n be some q1 into q2 into up to some q2j. Okay. So where q1, q2 are all prime numbers. Okay. Or all primes. So now the claim is that one of qi is of the form 4k plus 3. Okay. And do you see why that is?
We note that all of these are odd numbers.
These are all odd numbers because n is odd, so these are all going to be odd. But do you see why one of them has to be of the type 4k plus 3? Because if not, where you can go by contradiction, that if possible, let that not be true. So then let all qi be of the type 4k plus 1, or in other words, it's common to 1 modulo 4. Okay. So then the product of all the qi, so q1 into q2 into qs, qj, will also be 1 mod 4. Whereas clearly n is 3 mod 4, right? N, because it is remainder 3, so it's going to be 3 mod 4. So that's the contradiction. Okay, so I mean, Raghav, I think this was the only step remaining, that you have to prove that I mean, n can have a factor. N need not be a prime number, but even if n can be factorized, one of those factors is of the form 4k plus 3. And
Yes.
so that is the contradiction. So there are two possibilities: either that n is itself a new prime number of the type 4k plus 3, or there is a contradiction. Yes, Arnav, does that complete the proof or anything else?
Yes, sir. So if we get that the prime number divides 3, but I like why can't it be 3? I'm getting bit stuck there.
No, which step are you stuck?
Sir, after that, one of those should be of the form 4k plus 3.
Yes.
So one of them must belong to that list of which we had multiplied
Yes.
first.
So qi is
So from that we
basically
get that number divides 3.
yes.
So then why can't that number be 3?
Okay. No, I think we already shown that we are not taking 3 in this list, right? So this list has all numbers other than 3. Okay, I got
Okay,
your
sir.
point. Yeah, no, you have a point actually. So what if n is a power of 3? And what if n is 3 raised to something?
Yes,
Then,
something like that.
yeah, then there will be a problem. So the problem is, if you understand what is the problem here, so this qi is a element of this list. So qi is equal to some pk or some k. Okay, so whichever is the qi, which is of the form 4k plus 3, it is going to be equal to pk. So we have pk divides n, and pk divides the whole product, p4, p1, p2, etc., pt. And so when we subtract the 2, therefore we get pk divides the remaining term 3. So the only fact that that term is 3 is a problem. So can you think of some modification that, say, I want n to be of the form 4k plus, I mean, instead of remainder 3 modulo 4. So can I replace 3 by something else? Very small modification which will resolve this problem. Yes or no?
No, sir, no, sir. I was for
Okay,
PVC. I did not
I
get your
thought you
point
raised
for
that.
this one. Like,
Sir, would -1 help?
Yes, tell me.
So if you write plus, instead of +3, if you write -1.
Yeah, exactly. So why don't we define n as 4, this whole product minus 1? Then this problem will go away. It is still of the form 4k plus 3. It has still 3 mod 4. And now at the last step, what we'll get? N if pk divides n, pk divides the product. Therefore, pk divides 1. And which is a contradiction. So that will finish the problem.
yes, sir. This is
Yeah,
right.
okay.
This is
So yeah,
good.
that was the only change which was required. Okay, and I think on the similar lines, you can try to show the 6k plus pi sequence also. Again, it has a infinitely many primes in that sequence.
Yes, sir. Here again it will be odd, and that 6k plus 3 factor will be gone because then 3 will divide that number.
Correct.
But sir, how do we
Actually, as it
write
turns
this?
out, after a point, all primes are of the form either 6k plus 5 or 6k plus 1. I mean, if you ignore 3, every prime is of the form 6k plus minus 1 actually.
Yes.
So this can be leveraged for the same kind of. But the important in this lemma was this particular lemma that whenever you have a number which is of the type 4k plus 3, it cannot be composed of numbers which are all 1 mod 4. Okay, so one of those factors themselves has to be 3 mod 4. That was what helped to finish the problem. Okay, and I mean, I was just trying to read about this online. Turns out that so the Dirichlet's theorem is about arithmetic progression, right? Which is basically like a linear term, ak plus b. What about quadratic terms like ak square plus b? Or rather, I mean, the most simplest quadratic progression would be x square plus 1. Okay, so consider the sequence of numbers x square plus 1. So basically 1 square plus 1, 2 square plus 1, 3 square plus 1. Will this sequence also have infinitely many primes? As it turns out, this is an open problem. Nobody knows the answer to this problem. And I don't know, if some committee is going to offer a $1 million prize for that, you can try it. But at least for many decades, this has been an open problem. So even the simplest quadratic expression is unsolvable as of now. But in terms of linear arithmetic progressions, it has been completely solved using Dirichlet's property. So yeah, interesting that how just changing. So instead of writing this 2 as an exponent, if I write it as 2x plus 1, we know how to do that. But if I just take this 2 and put it as an exponent, suddenly the problem becomes open-ended, which nobody knows the answer. So yeah. Okay, so I think actually there are a few other interesting properties about prime distribution which not useful for Olympiad as such, but you may be curious to know that how are prime distributed. So as it turns out, like for any number n, the question is how many primes. I mean, what we show here is there are infinitely many primes, but how are they distributed? In general, we expect that as a number becomes larger and larger, it is much more likely to be a composite number, right? Because it has to sort of dodge so many prime numbers. So the chance of a number being prime keeps going down and down. So how many primes are there in the set 1, 2 up to n? Okay. So I think there's some notation for that, but turns out that in most cases, log of n is a very good approximation to this number. So the logarithm of n is a very good approximation to how many such primes are there. This is a particular called a prime number theorem. I forgot the name of that, but I think this is given as a appendix for Burton. So if you're interested to know how this theorem comes about, you can look at the appendix of Burton. So this is one property which can be useful sometimes. There's one more much more practical property that for all n, there exists a prime in the range n comma 2 n. So any number and its double in this range, you are always guaranteed to find out a prime number. Okay. Again, I don't think I've never tried to come across a proof of this, but maybe you can try to Google and see if there is something available. So I mean, in terms of problem solving, this is a much more practical property which can be useful in some problems that in any number n and 2n, there exists a prime number. So you are free to use this without proof. Even if we don't know the proof of it, it's a well-known property. Okay. And I think Burton, they also dedicated a whole chapter to the C of Eratosthenes, but I'm going to skip that because, I mean, to some extent, it's also treated in school mathematics, and I think you can formalize it on your own. And basic observation is that it's enough to check the prime numbers up to square root of n to check if the number is a prime number. Okay.
Also, there is the property about like arbitrariness of positions of primes, right? Like there are n for any n you can get n consecutive prime number composite numbers.
Yes, you can get n composite number using the factorial trick, right?
Yes,
So if you have
n plus 1 factorial plus 2 plus 3 plus 4
yes,
plus
correct. So if you have n factorial plus 2, n factorial plus 3, up to n factorial plus n. So this whole list is a set of all of them are composite numbers, and you can see that I can make n as large as possible. So this is an entire sequence of n minus 1 composite numbers with no break in between. So I can keep getting such a larger and larger sequence. Of course, the n itself keeps increasing each case. So you have to go much larger and larger to find the sequence of such consecutive composite numbers, but you can always find them. Yeah, I think in terms of theory, this is all that we need to know about prime numbers. Now it's all about applying for various problems, and in fact, like now you'll see how prime numbers and congruences can be used together. So we'll have things like Fermat's theorem and things like that. So I think I'll leave all of that for the next lecture. For now, just give me a couple of minutes if I can search for some problems for us to practice. Okay, I'm not able to find the property problem, but actually there's one more thing I'd like to mention about prime numbers. It's very, very interesting. Again, this is more like general knowledge, but to understand how prime numbers are distributed. So if you consider the reciprocals of numbers, right? So if you consider numbers such as 1 upon 1 plus 1 upon 2 plus 1 upon 3 plus, so this infinite sequence of reciprocals. So I mean, you can take Sn equal to the first n reciprocal. Okay? So Sn equal to 1 upon 1 plus 1 upon 2 up to 1 upon n. So as you can see, for every subsequent term, Sn plus 1 is just going to be Sn plus 1 more reciprocal. And as n becomes larger and larger, the reciprocal which I'm adding is a very small quantity. So the question is naturally, how big can Sn become? So does anybody know what happens to Sn? So I mean, we don't have calculus at our hand, but if abuse of notation that as n becomes infinitely large, what is the limiting value of Sn? Because if you draw it like a graph, it will be look like something like this. Like the first jump is very big, the next jump is smaller, the third jump is even smaller and smaller and smaller. So it will keep on looking like this. It will become more and more flat. It will never become completely flat. But the question is this there is some upper bound, that there is some limit that this sequence will never cross this limit? Or is it that if you take a sufficiently large value of n, this black sequence will cross that boundary, any boundary that you set? Okay. So if you have not thought about this problem, this is a good time to think about this and understand that there are sequences where this is bounded. So see, Sn was defined in this way. Let me define one more sequence, Bn, which is the same thing but only in powers of 2. So let Bn be the sum of the first n powers of 2.
Sir, I actually know the solution to this problem.
Okay, then maybe let's give others a chance.
Yes, sir.
So, and before you look at Sn, consider the sequence Bn, okay, where every term you add a reciprocal of the power of 2. Okay. So B1 is simply 1 upon 2 raised to 0 plus 1 upon 2 raised to 1, which is 1 plus half. Okay. B2 will be, you will add 1/4 to that, so plus 1/4. So this is 7 by 8. B3 will be 15 by 16. So in fact, I think you can come up with the formula for Bn, right? Because this is just a geometric progression. So the Bn will turn out to be nothing but 2 raised to n plus 1 upon 2 raised to n plus 1. So this sequence, oh, I think I'm in a mistake. Actually, 15 upon. So 2 raised to n plus 1 upon 2 raised to 1. Okay. So this is the value of Bn, and I think we can all clearly see that. So Bn will also keep increasing, but it can be never exceed 2. Okay, so Bn truly looks like this. So if I draw a graph, let's say this is the value of 2, then the Bn will look something like this. It will never cross this limit of 2, no matter how big value you take. But in the for Sn, the question is, can you take sufficiently large value of n to cross any limit that you set?
I have sent to the basic idea of solution in chat.
Okay, I'll just check. Yes, yeah, that is the right idea. Okay, so as it turns out, actually Sn is what we call divergent. So Sn is divergent. And the meaning of the word divergent is that Sn can be made as large as you want. So no matter which limit you set, and this can be very surprising, that looks like the contribution of every next term will be even smaller and smaller because we are adding a reciprocal, right? So, but turns out that you can make Sn as large as you want. Okay, and the proof of it goes something like this. So if you consider the terms, I can split Sn as groups of powers of 2. So 1 upon 1 plus 1 upon 2 plus 1 upon 3. Okay, so what happens if I group it this way? Okay, so every power of 2, so the next group will be 1 upon 8 to 1 upon 15. Okay, so this is how I group up till whatever is, there will be some leftover terms at the end which I'm ignoring. But if I group it this way and you look at it one bracket at a time, okay, you'll see that in every bracket, so see every bracket is of the form, it starts with the power of 2 and it ends just before the next power of 2. Okay. So term by term, if you compare each term over here, I think we all know that if a number is smaller than if p is less than q, then the reciprocal is reverse. 1 upon p is greater than 1 upon q. So in that way, each of these terms, the denominator are all less than 2 raised to n plus 1. Therefore, I can say 1 upon 2 raised to n will be greater than 1 upon 2 raised to n plus 1. And same way for every term. Okay. So all of these terms, there are 2 raised to n such terms, right? So if I add up all of these sequences, the last will be 2 raised to n plus 1 minus 1 greater than 1 upon 2 raised to n plus 1. So if I add up all of these inequalities, what I'll get is RHS will simply 2 raised to n times 1 upon 2 raised to n plus 1, which is half. So what I'm saying is that the sum of this LHS is greater than half, which means term by term, like bracket by bracket, this bracket will be guaranteed to be greater than half. This bracket will be guaranteed to be greater than half, etc. This bracket will be greater than half. So if you keep adding half multiple times, obviously that sequence we all understand is keep on growing, right? So if I want Sn to cross, let's say 10, I just need 20 such half. So if I consider n to be 2 raised to 20, then Sn will be guaranteed to be greater than 10 or something like that. Okay, so half plus half plus half will guaranteed to exceed any limit that you can set. So therefore, Sn can be made arbitrarily large. Okay, so in other words, what we say is sigma or Sn is divergent, or more compactly, what we say is sigma 1 by n is divergent. Now this is the surprise. Sigma 1 by p is divergent, where p is all primes. In other words, if I keep adding primes, so 1 upon 2 plus 1 upon 3 plus 1 upon 5 plus 1 upon 7. See, logically, we know that primes are going to be so rare. If you take larger and larger values, as Arnav said earlier, you can find very large sequences where there are no prime numbers. So the prime numbers are going to be so infrequent. At some point, you're going to add such a small reciprocal. So if you add pk at one point, the next prime number will be maybe much farther, pk plus 1. But this sigma 1 by p is also divergent, which means that you can make this as large as you can. Actually, it turns out you know enough to prove this at this point. So I'll leave this as exercise for you to try and prove this. And prove that sigma 1 by p is divergent. I'll not give you a hint about how to do that, but just think about it. But it's such a surprising property that although primes are really rare, but they are not that rare. They come sufficiently frequently to make sure that this sum can be made as large as possible. And turns out that this is one more way of proving that primes are infinite. That a bit more complex proof, but if you prove that this sequence is divergent, then by definition it has to mean that the set of primes is infinite. Because if otherwise the set was finite, then this sum will stop at some point. The fact that this sum does not stop is another proof that the primes are infinite. But that is a bit more unconventional approach, so I won't go into that. Okay, but I mean there are a lot of sort of nice tricks and general information about prime numbers which are useful to know. Not all of this is useful for problem solving as such, but see, this is why it's useful to study theory, because within the theory there are many techniques which can be useful for problem solving. So when we show that Sn is divergent, we use this grouping technique. That grouping technique could be useful in some Olympiad problem. So that is how you can start to look at the theory as ways to develop your own problem solving tools. Okay, so that's why it's important to pay attention to this. So we have 15 minutes left, but actually my throat is not very well, so I won't be able to continue talking for much. So I plan to cut short today's lecture. So for next lecture, I'll plan to continue with more properties of prime numbers, particularly Fermat's little theorem and things like that. And importantly, I will come back with some p-adic valuation information also. Okay. Yes, I think that's all for today. Just one thing I want to add related to the practice problems that we had done. So, no idea. Okay. So the practice papers which all of you wrote, right? I have some general feedback about what you need to improve. These are things which I already said before, but just want to repeat them and make sure you pay attention to these things when you solve more problems. So one thing which is common to many of the solutions is that you have to make the intention clear about what you're trying to solve. So basically, it is like whenever you are, let's say, you are applying induction, always start with the main claim that this is the we are applying induction on N, and then proceed with the details. Okay, if you directly jump into the induction hypothesis without explaining that this is what you are doing, the examiner will be lost. So always start your proof with this is like write your strategy first and then go into the details. So the examiner has a clear idea of what you're trying to solve or where you're trying to go. Because then even if you make some minor mistake in the details, you can still the examiner knows where you're trying to go. So you can give you partial credit based on that. But if you just keep writing equations without making your strategy clear, then the examiner doesn't know what you're trying to reach. Because see, partial marks evaluation in Olympiads is done in this way that if there is some known complete solution and you are proceeding along those lines and you reach some 5 out of the 7 steps, then we can give you the marks accordingly. But if you are just writing equations which we don't know leads to a valid solution, then we cannot give it any credit at all. Okay? So that is how the partial marking is done. So it's important to state your strategy very clear upfront. Other things which I already said last time were that don't try too much and don't try too little. So this is something that you will be able to judge better with more practice. But don't spend your time writing proofs of the trivial statement. So things which we can assume without proof, you can just assume and go ahead. So all the basic properties which you find in the book, such as Burton, you don't have to keep proving them. Okay, so you can just use the property and move on. In fact, you can also use some bigger properties from higher standards, such as calculus, etc. Can also be used without proof, but you have to be careful that you are satisfying all the conditions in the given question. So, I mean, if you use any ideas such as continuation or differentiability, you have to make sure that the conditions are satisfied by the problem. Only then you are allowed to use those things. Okay? In general, about solving the problem themselves, and I urge this every time, always try simple approaches before hard approaches. Okay? Because many times the Olympiad problems, the way they are designed is that we want them to be approachable by 9th standard students also. So always there will be some simple approach which uses elementary ideas. Like for example, in number theory, a simple idea is divisibility and bounds estimation, and harder, difficult technique could be p-adic valuation. So first think about simple approaches before you try something harder. Okay, because I mean you might end up making the problem much more harder for yourself. then I think I need to go back and look at your papers in more detail. But one more thing which I observed is that diagrams have to be much more well drawn. So in particular for geometry, we had, I don't know, did we have a subjective geometry question this time? Probably not. But if you have a subjective geometry question, it is very important to draw a clean diagram. Draw a non-isosceles triangle. Wherever you have a triangle, try to go for the most general case possible. Okay, don't try to draw an isosceles or equilateral looking triangle and try to make conjectures there, because that will mislead you many times. So try to take the most general case possible and draw the diagram for that. Same is applicable for any such like generalization. Like if you have 3 points, random points in the plane, try to take them as non-collinear as possible. Okay. Also, turns out that you can draw the diagram in multiple ways. A very common example of this is the excenter incenter configuration, which all of us know. So if you are to draw all the incenters and the excenters, if you start with triangle ABC, actually my tablet is not working together. I'd like to show this also. But see, imagine what will happen if you start with a triangle ABC, and then from that you try to construct the excenter. Often the excenters might go out of page if you have not started the initial points correctly, right? You must have observed this happening. So what is the fix for this? Nobody is asking you to start from the ABC triangle. Why don't you start with the excenter? So first draw the excenters I1, I2, I3. And from the properties, we know that the ABC are the feet of the altitude. So you can draw ABC inside the outer triangle I1, I2, I3. So always keep in mind that what the question gives you the starting point doesn't have to be your starting point. You can start with a completely different set of initial objects and still construct the diagram you need. Okay. So always keep these possibilities in mind. I think those are all the points which I can think of right now. Maybe as I said that you are always welcome to send me some problems. If you are solving any practice problem from somewhere and you've written your solution, do post it on WhatsApp. You can send it on the group, or you can send it to me on personal WhatsApp also. So I can take a look and try to give you some feedback. But I mean, this has to be a continuous process. It's not like I'll try to keep an exam once every month, but even in between, it would be good for you to keep practicing writing solutions in all the topics. Okay, so that is primarily what I can suggest for you. Okay, I think we'll end the lecture early today, if that's all.
Thank you, sir. Bye, sir.
Okay, thank you. Bye.
Excuse me, sir.
Hi, sir. Thank you, sir.
Excuse me, sir.
Yeah, sure.
Yes, sir. I wanted to ask, like, in the exam, what was the highest marks that we know that, like, where we stand?
Are you asking in the practice problem or in the
Yeah,
general?
no, in the practice test.
In the practice test, I don't have the list of full scores here, but in general, I mean, if you ask where you stand, if you are scoring more than 30 marks in this special, this is my judgment, then you are in good position to do well in IOQM as well as have a decent chance at INMO. So that is a benchmark which I can estimate. But of course, I think to the most extent, my problems are on the simpler side, particularly in the first 4 subjective or the objective numbers which we had, right? Questions 1 to 4. I think you can expect much harder difficulty in IOQM, because finally, as you know, the exam structure this time, IOQM is going to replace IOQM plus RMO. So you can expect RMO difficulty problems also in IOQM. So in fact, next paper I'll try to set harder problems for your practice.
Okay, sir.
Okay, thank you.
Thanks.
Bye.